In the previous chapters, we have seen bending stress distribution as well as shear stress distribution in case of bending. Now, before starting torsion chapter, first we have to understand in which cases we will be getting this torsion. Okay. So, the load which we are applying is same, exactly same, whether you want to bend it or twist it. The load which you are applying because of gravity is exactly the same. Whether the load will twist the beam or it will bend the beam. So, how to identify that? Many students will often confuse with this. So, how to identify that? First, we will discuss that and we will discuss about torsional stress distribution. Okay. Okay. So, already we discussed that for every cross section we will be having three principal axes x, y and z. So, in that only one will be the longitudinal axis or torsional axis. So, about one axis, if your load is eccentric, the beam will twist. About the remaining two axes, if the load is eccentric, it will bend. So, how to identify that axis? How to identify whether the load you are applying will twist the beam or bend the beam? So, how to identify that? Let me tell you one example. You may think it is very easy. Let me tell you an example. Here you see a spring. Okay, this spring, the name of the spring is closely coiled spring. You will know this in springs chapters exclusively. There are various formulas you do remember for this, but in this chapter there is one thing important you have to know about this, because the formula which you are studying now, you will apply this exactly in torsional springs. Okay. So, while applying, you just see that when you are applying a load W for this spring, how this load is looking to you? Is it looking like a axial load or is it looking like a eccentric load? It is passing through the center here. It is passing through the center exactly, the load. Okay, so the spring is like this. Okay, somewhere in the center the load you have W. Okay, so you may think it is, as the spring is like this, it is looking like a axial load W. Okay, these two are not same. This load will actually create torsion in this. That is the reason closely coiled springs, also known as torsional springs. Okay. When you come to open coiled, it will have torsion and bending as well. Okay, we will discuss this that also in this class only. But first you have to understand, we cannot really easily imagine. So, when we are extending a spring axially, the moment may look it is loading axially, but every cross section will rotate or will twist to get that axial pull. The pull looks like it is moving axially, but the spring actually got twists. Okay, because of the twist, combined twist effect you are getting at the bottom axially, but that is not the axial load. Okay, even though you are applying the load axially along this axis, that load will not create only axial load, it will also create torsional stress in this. Okay, so how it will create? So how to identify such torsion? Let us see. Generally, when we say torsion, in your mind you will get some picture like we are twisting like this. Even in books, generally we will see a torsional moment something like this for a beam. But in reality, we do not really apply a couple like this. Whatever the gravity load we are applying, that will create the twist. We do not really apply the torsion like this. Okay. If it is in mechanical devices where you have shafts, there we will apply that. There also we do not apply the couple directly. We apply the couple using the load only, right? So, how to identify this torsional load? How to identify whether a load will create bending or whether a load will create torsion? Let us see. Okay. So, for this, first, as I already told you, every cross section will have three axes. Okay. For a symmetrical section, x, y and z axis are principal axis directly. Okay. So, if I take a rectangular beam like this, so if I take a rectangular beam like this and load at the center, from the top view, this is the cross section. The cross section is rectangle. In the top area plan, the beam is supported like this. Okay. So if I am loading at the center I mean, okay, not at the midpoint, with respect to the width whatever you have at a distance b by 2 I am saying. I am not saying I am applying the load at L by 2. If I am applying the load at B by 2 exactly at the center somewhere here, if I apply the load, then this will create only bending. If I apply the load apart from center, I don't know whether you are able to look this or not. Okay, so I hope you, so this is the plan view. Apart from the center, if I apply the load at any other point apart from B by 2. So if this is B, this is B by 2. Apart from this, if I apply the load at any point on the beam like this, it will create torsion along with the bending. Okay, so the same load whatever you are applying, can create the torsion as well as bending. Okay, we simply draw the loading like this, but whether this load is passing through the B by 2 or not passing through the B by 2, we generally don't mention. Actually we have to mention it. By default we assume that it is passing through the centroid of the cross section. Where you are applying the load, if it passes through that centroid, then it will create only bending. Okay, otherwise it will create torsion as well as bending. Okay, so how to identify? So here it is creating torsion, here also it is creating torsion, and one more case if we observe, here you see a cantilever slab. So for cantilever slab, here you have a beam, right? This beam is also subjected to torsion. Okay, so how to identify this? So to identify this, I will tell you two rules which you have to remember. Okay, that will simplify the procedure of identifying the torsion and bending axis. Okay, so first what is eccentricity? We are telling we are rotating, because of the load it is creating a moment. What is moment? Force into perpendicular distance to the axis. Okay, that perpendicular distance is known as eccentricity. Okay, okay, now I have two axes here. I am applying a load, I have three axes. Okay, so because of this load whatever I am applying, whether if I see the distance E from this axis and the same distance E from this axis as well, about which axis exactly I am applying? From both the axes it looks like perpendicular distance. From both axes it looks like perpendicular distance. I will tell you here. See here I am applying a load. Okay, here I have two axes. From the two axes the eccentricity is E only, but I am applying with respect to x axis or y axis or z axis, longitudinal axis. So about which axis I am applying the moment. So how can I identify this? Okay, so to identify this, first you have to follow the rules. Load line will not be parallel to the rotational axis. What is load line? You are applying a force, right? A line extended along the load is called load line or force line. Both are same, load line or force line. Okay, so load line will not be parallel to the rotational axis. Second rule, load line will not meet the axis. There are two rules for you to identify. So these two rules will simplify you to identify about which axis it is rotating. First you will be able to find whether it is rotating about one axis or two axis or both the axis. Okay, right. So first you will identify about which axis it is actually rotating, about first or second or both. Next, whether that axis will create bending or not. To identify that, first thing you have to identify the cross section. This is very important. In case of springs, whatever I told you, the first thing you have to know is what is the cross section for that beam. Okay, anyway it is not a beam. Generally for the structural element, what is the cross section for the load whatever we are applying, what is the cross section? That is very important. Generally we think the longer circle is cross section, but no, the shorter circle is the cross section. How to identify that? We will tell you. First thing is identify the cross section. Second, find the longitudinal axis. Find the longitudinal axis. After finding the longitudinal axis, if axis of rotation is longitudinal, Okay, first identify the cross section. Once you identify the cross section, we will get what is the longitudinal axis. How we will get the longitudinal axis? We will tell you a small definition to that, you will easily identify it. Next, if you came to know that this axis which you found is longitudinal axis, then it should be torsion. If it is not longitudinal, then it is bending. Whether it is x or y does not matter. Whether it is z or not, that is all. About one axis only which is along the length, we will be having torsion. Okay. So now what is this longitudinal axis? Okay. The definition of longitudinal axis is simple. Okay, axis which cut the cross section at single point. Already you identified the cross section. The axis which cut the cross section at single point. Okay. So I already showed you the beam with three axes. One axis will be inside the beam which you cannot see. This will be along the pin like this. Okay. This will be the z axis along the pin. Okay. Now what is the longitudinal axis here? This is the cross section. You see this axis, it is cutting more than one point. You can identify the axis at more than one point. Even y axis you can identify more than one point. But if you see the z axis, it is touching only one point in the entire cross section. This is the best way to identify longitudinal cross section. Okay. Once you identify the cross section, among the three axes, one axis will touch only single point in the cross section. Okay. Or axis perpendicular to the cross section, axis which is along the length, you can remember in any way. Okay. This is one of the best way to remember. Okay. Or axis perpendicular to the cross section or axis along the length. That is why it is called as longitudinal axis. Okay. So which are along lateral section, they are called as lateral axis. This is called longitudinal axis. Okay. Okay. Now how we can apply these rules? Let us see. Okay. See, in structural analysis, identifying everything is very important. In previous classes also, if you remember, we told you for diamond section, see, this is a square section, not rectangular section, this is a square section. If you are bending a square section with a moment, some x moment is required to fail this. Just by rotating it 45 degrees, I can save 30% of the moment to fail this. Okay, if I want to fail. If I want to fail or if I want to break this easily, just by rotating, I can save 30% of the effort. Why? The diamond section is √2 times lesser compared to square in bending. Just by rotating, I am not changing material, I am not changing load, anything. Just by rotating, which is a diamond section, just by rotating, I can save 30%. Why? 1 by √2 is 0.7. 0.7 means diamond strength is 1 by √2 times of square. 1 by √2 is 0.7. So 0.7 times of square means 30% lesser effort I need. The moment that is required to fail a diamond section is 30% less compared to square section, just because of rotation. Why? Why? Because more particles are close to the center compared to square, more particles coming closer to the center, which reduces its moment of resistance. Okay. Okay. So anyway, let's come back to the topic. Okay. So how to identify this? Already I told you two rules. So suppose if we are applying the load slightly away from the center for any cross section along the length, if you are applying a load slightly away, then what happens? So for a simply supported beam, okay, you have applied the load, but it is slightly away from the center, okay, not passing through the centroid of the cross section. Okay. Now let us draw the three cross sections for this. Let us draw the three cross sections for this. Sorry, for the cross section, let us draw the three axes for this. So this is longitudinal axis, because first step is to identify the cross section. This is the cross section I am considering. You can consider any cross section you want, whatever the cross section you want, you consider. Okay. So this is the cross section. Okay. Okay. Now for the cross section I have to draw 3 axes. Okay. This is one axis, this is one axis, and this is one axis. Along my pen I have one axis. Okay. Okay. So 1, 2 and 3 axis. First rule, the load should not be parallel to the load line. Particularly load line means line extended along the load. Okay. The load line should not be parallel to the axis. So actually this load is not creating any moment about this axis. Next, the load line should not meet the axis. Is it meeting the longitudinal axis? It looks like it is meeting, but actually it is not meeting. Why? Because the centroid is here. I am applying the load here. Okay, in the front view it looks like it is meeting, but it is not really meeting. You can see it is not meeting. The longitudinal axis will be passing through this. So it is not meeting. Okay. Next, with respect to x-axis, is it meeting? No. Is it parallel? No. So with respect to x-axis, it is not meeting, not parallel. With respect to z-axis, it is not meeting, not parallel. Okay. So this load will create this is breadth and this is length. Okay. You are applying the load slightly away. Because front view alone is not sufficient for you to understand this. Okay. So this load is creating torsion plus bending. What is the amount of torsion it is getting? Let me write it as MT. What is the eccentricity you have here? Let me call it as EZ, and the eccentricity to this, let me call it as EX. Okay. So EX EZ into P or P into EZ, PEZ, and MX P into EX. Okay. So in this way we have to identify. So suppose if it is passing through the center, okay, if it is passing through the center, okay, then it will create only bending, no torsion. It will create only bending, no torsion. Okay. So draw the load line, okay, meeting the longitudinal axis at the center. You can see here, previously here in the top you can see it is not meeting. Okay, not meeting, not parallel. Okay. So here meeting, even though it is not parallel, it is meeting, and with respect to y axis if you observe, it is parallel. Okay. So it is creating only bending about x axis. What is x axis? What is x? So here I am applying a load. Okay. In this identify the bending axis because of this. Okay. Actually the beam is like this. I applied a load like this. Identify about which axis it is bending. This y axis is parallel to the load line. So it is not bending about y axis. It is bending about x axis. This. Okay. For this beam there are 3 axes, right? This is x, y, z. It is rotating about x axis. The bend whatever you have is about x axis. Okay, the rotation is about x axis. Okay. If it is with respect to z, it will get twisted. With respect to z, it has to twist. So if you place a load here, it will bend. If you place the load slightly away, it will bend and twist. What will happen? It will bend and twist because of the torsion you are applying. Okay. So this is I hope you understood for the beam. Similarly, if you have a column or compression member, okay, circular column, whatever it is. Okay, because for beams generally we don't see circle. Already we discussed circle and square and rectangle strength comparisons. So if you see rectangle is stronger compared to rectangle, I section is much stronger because more particles are away from the center. Okay. So I section means it looks like this. It looks like this. Okay, this is the best section. This is the best section for bending. Why? Because we have more particles away from the center, less particles towards the center. Okay, bending stress will be maximum at extreme fibers. So we should have more particles in the extreme, less particles. So even if you see the diamond section, if you see the diamond section, why the strength is less? The strength is less because where you have more stress, there you have less particles. Okay, so obviously the strength will get reduced. So the same material, just by changing the distribution of particle or just by changing the orientation of the body, you will get huge amount of strength just because of orientations. Okay, so just because of shape, arrangement of particles, orientation, everything matters. Okay, so already we have seen circular shape. So circular shape, so circle is to square. If you compare the area, circle requires 1.18 times. So around 18% extra area we require to get the same moment of resistance. So generally we don't use circular beams. Okay, for columns, circles we can use. Why? We will see in compression members. Okay, compression member topic. Anyway, so for a circle, you don't have lateral loads. You will have longitudinal loads for this. Okay, first identify the cross section. So I am applying a load like this. What is my cross section? This is my cross section. Circle. Circle is my cross section. Okay. Okay. For the circle, suppose if I am applying a load, first I will tell you this case. If I apply a load, it is purely axial. Okay, no need to explain for that. Suppose if I am applying a load somewhere here. Okay, for a compression members, instead of center, I will apply slightly away from the center. Okay, now what is my longitudinal axis here? First I identified the cross section. This is touching more than one point. This is also touching more than one point in the cross section. Now if you see the cross section along the length, it is touching only at one point. It is touching the cross section only at the one point. So this is my longitudinal section which is along the length. Okay, through the centroid, the principal axis, three principal axis will be there that is passing through the centroid. Okay. Okay. So now the load is applied here. Okay. Now the load is applied here. Let us apply the rules. Okay. The load is like this. You are able to understand now. It is meeting this axis, so it cannot be eccentric about this, and it is parallel to this axis, longitudinal. Okay. So if I apply a load to this, it is parallel to the load line is parallel to the longitudinal axis. The load line is parallel to the longitudinal axis. So obviously it won't create torsion. Okay. Wherever you apply axial load on the column, it cannot create torsion. Why? Why? Because wherever you apply, it becomes parallel to longitudinal. So it's not possible to create torsion on the column. Yes, it is possible. Not with gravity load, but with wind load. See, if this is the column and I apply a load like this, away from the center, not if I apply exactly at the center, it will meet the torsional axis. Okay, slightly away from the center if I apply, now you can see this load is not parallel to the longitudinal axis, not meeting the longitudinal axis. So this wind will actually twist the column. So earthquake waves as well as wind load actually create torsion in column. Axial load cannot create torsion on the column. That is applied on the column I am telling you. Okay. So if you apply the load on the slab which generates a couple and couple directly apply on the column, then there is a possibility of creating torsion. That is secondary. Directly if you are applying axial load on the column, in that case only I am telling you. Okay, I am not telling you because of gravity you cannot get. You can get indirectly from the slab. From the slab you can transfer. That case also I will show you. Okay. So directly by applying the gravity load on the column, you cannot get torsion because it is parallel. But because of wind load you can get the torsion. Okay. So in this case, it is only bending because it is parallel to the torsional axis. Bending about which axis? Let me call it as x and y. It is meeting the x axis, so the answer is y. Myy is equal to P into Ey. Let me call this as Ey. Okay. Now if the load is here, and let me call this as Ex, distance to the x axis. So the moment generated is P into Ex. Same logic, I am not explaining again. Next, sorry, xxy. If I am applying a load somewhere here, this is Ex and this is Ey to the axis. Now you see this load, it is not meeting x axis, not parallel to x axis, not meeting y axis, not parallel to x axis, but parallel to longitudinal axis. So directly I can remove torsion. Wherever it is applying, it will not create torsion, as I already told you. So it will create bending about two axes. The same beam will bend about x axis as well as y axis. So Mxx is equal to P into x, Myy is equal to P into Ey. Okay. So if you take a beam and bend along y axis as well as along x and y, this is bending about x, this is bending about y. If this is y axis, you have to bending like this or like this. Okay. So if it is bending about x and y, that is called as biaxial bending. We will know this in compression members as well, but still not subjected to torsion. Okay. So compression member subjected to torsion is beyond your syllabus. Okay. Especially in earthquake design, we will be getting that. Okay. Okay. Now we will come back to the same position where we have started, that is spring. Okay. For spring, the main problem is to identify the cross section. Okay. So to identify this cross section, I will tell you one hint. See, when you extend the cross section, whatever identified, when you extend the cross section along the length, then you should get the entire body. This is a hint to identify cross section in complex situations. Okay. When you extend cross section along the length or longitudinal axis, both are same, along the longitudinal axis, then you should get entire body. What does it mean? What does it mean? So for the same beam, I have shown you, this is my cross section. So if I extend the cross section along the length, I got the entire body. If I extend the cross section, just like in SketchUp how we drag along the length, so by drawing a cross section and drag along the length, I got the entire body. So this is my cross section, verified. Okay. So identify the cross section, drag along the length, you got the entire body, true. Rectangular cross section, identify the cross section, drag along the length, you got the cross section. Cross section, length, you got the cross section. Okay. Now let us see for the spring. Okay. So you may be thinking, this is your cross section which is slightly inclined. Okay. So closely coiled spring generally means the inclination, this helix angle, this is called as helix angle, which is less than 10%. We say it as closely coiled, or we assume there is no inclination here. Okay, almost straight line. Okay, so you assume it is almost straight. You assume it is almost straight, but still, if you extend this along the length, if this is your cross section, this has to be your longitudinal section, which is cutting the cross section at single point. So if you extend it along the length, you will be getting a cylinder, not spring, because you can see there are gaps. So the cross section you identified is wrong. Now I will show you the cross section. For the spring, you have a thickness cylinder, you have a small thickness of the spring right here. Throughout the length, there is a small diameter. That is your cross section. That is your cross section. So if you extend this along the length, if you extend the cross section along the length, you get the entire body. You may ask me, why you change the direction of length or longitudinal axis? Yes, the direction of longitudinal actually changes. I did not change it. The longitudinal axis direction is not constant for spring. It changes at every level. Every level. So if this is the spring I am taking, at this cross section, this is my longitudinal axis. At this cross section, this is my longitudinal axis. At this cross section, this is my longitudinal axis. At this cross section, this is my longitudinal. So the longitudinal axis direction changes along the length like this. Okay? It is not a single line which goes throughout every cross section. For every cross section, because this is your cross section which is traveling like this, for every cross section the longitudinal axis direction changes in case of spring. Okay, now you got what is the cross section of spring, right? So for the cross section of spring, you are applying a load somewhere at the center in 3D. Okay, just for understanding I am telling you, imagine this is a spring, even though it is a circle, imagine as a spring, and you are applying a load here. Okay, you are applying load at the center, right? So when you are applying the load at the center and this is your longitudinal axis, let me find any one point. Okay, so at this point this is my longitudinal axis anywhere. So this longitudinal axis is not meeting the load line because the load line is at the center, not parallel. Okay, this is not meeting, not parallel. Obviously it creates torsion. If you imagine this as a straight line, instead of inclination, if you imagine this like a straight line, then see the other two axes. This will become y because you imagined as straight, parallel to the load line. I can remove y. Next, another is x axis. As this is straight line, perpendicular axis will meet the load line. So it is subjected to pure torsion. It is subjected to pure torsion. If I assume any inclination, then the axis will not become parallel. So it is subjected to bending. So a closely coiled spring, if you assume this as a straight line, closely coiled means even though it has 10 degrees inclination, we assume it as a straight line. So if you assume it as a straight line, obviously for the straight line, this axis will become parallel, this axis will meet the load line along the length. Okay, so that's why we say for a closely coiled spring, you won't get bending. Okay, only torsion. For open coiled, which is having inclination more than 10 degrees, we call it as it is subjected to torsion as well as bending. Okay, so when a closely coiled spring is stretched, every layer of the spring gets twisted to a different amount. Okay, so not different amount because for load into eccentricity, if you observe, it looks like same. Okay, the amount of torsion you apply is same, the amount of rotation is different because this rotation accumulates to next level. Okay, the amount of torsion you apply is same because load into eccentricity. So everything is at a distance of small r. Everything is at a distance of r, but the amount of rotation varies from one section to other because this rotation will accumulate next level and combined rotation whatever you have will apply at the bottom and it goes down. Okay, so actually the twist is giving you the axial pull. The entire spring is not moving axially. The entire spring is twisting and that combined twist is shown axially. Okay, that is what happens in helical spring. Okay, so I hope now you understood how to identify the torsional axis and what is exactly torsion. Okay, now suppose if you see a cantilever beam like this, okay, you can assume this as some canopy slab, okay, for canopy slab you are applying a load on the slab on the top, right? So if you are applying the load on the top somewhere at the center, because for entire slab the load will be acting somewhere at the center, right? You can see previously whatever the slab I have shown you, the load will be acting somewhere here which is away from the longitudinal axis I told you, even if you just move your load slightly away from the center, you will get twist. Now the load is somewhere here, obviously it will create torsion. So canopy beams and cantilever beams where you have balconies, that also will be subjected to torsion. Okay. One more example we can say is water tanks. Water tanks. In water tanks, we will be having ring beams. Ring beams. The water load coming at the center. Okay. So this beam, this ring beam, obviously it is not circle, it is ring beam. Okay. So for this ring beam, just like spring, at every point the longitudinal axis will change. Here the longitudinal axis is like this. So this is the longitudinal axis throughout the length. This is the load from the water because of gravity. Okay. So I can see the longitudinal axis is not meeting, not parallel. So the entire ring beam will twist like this because of the load. The entire beam through ring beam gets twisted. So ring beam also gets torsion. Okay. This ring beam has another name, another category, that is known as beams curved in plan. Means generally if you see in elevation, we may see a curve. Okay. But it is beam curved in plan. If you see from the top, it should look like a curve. Okay. That is called beam curved in plan. That is also another category which is out of your syllabus. Okay. But that is one of the good example we can see where you are getting torsion. Okay. So now let us see some examples which we already explained. So this is the center. So if you apply the load here, you get the torsion. Helical spring already we explained. Now you see this case. Suppose if you apply a load here. Okay, there are two beams here, you can see. One beam is like this, another beam is like this. So if you apply a load like this, for this beam, this is the longitudinal axis. So it creates only bending but no torsion, because for this beam this is meeting the longitudinal axis. But for this beam, this is the longitudinal axis. Okay. Now if you see the load, this is not meeting the longitudinal axis, not parallel to the longitudinal axis. So this beam is subjected to bending, whereas this beam is subjected to bending as well as torsion. Why it is subjected to bending? Because of this load, obviously it is subjected to bending now. Wherever you take the cross section, see this is the x-axis. Okay, it is not meeting, not parallel x-axis, that is by default we will be knowing the bending. Okay. So it is eccentric about x-axis and eccentric about z-axis as well. Okay. So if you want to feel this, imagine there is a rod like this, another rod like this. If I apply a load like this, this will simply bend, but for this it will get twisted and bent. Okay, you can feel it, right? Okay. So this is just like a lever arm. Okay. So if you apply a load, obviously this will bend as well as twist. Because of this load, it will get twisted. Okay. So in this way, when you have group of beams, okay. Now let us see one example to understand torsion and bending. Just by changing the load, how the bending and torsion will change, we will see now. So imagine there is a frame something like this, okay, with a load downward like this. Okay. See here you have three beams. These three beams will be subjected to three different loads, you see, depending on our trick. So first for this beam, so let me call this as A, B, C, D. Okay. So first for this beam, identify a cross section anywhere apart from the load line, because when you take cross section at the load line, it will go through the centroid and there will be no eccentricity. Okay, you can take any other cross section somewhere here. Okay. Now this will be my y axis. For this cross section, this is my longitudinal axis and this is x axis. Okay. So now if you see the load line, this load line is parallel to y axis, so this cannot create torsion. It is meeting z axis, so it cannot create torsion. Okay. So this cannot create bending about y, torsion about z, because it is parallel and meeting. Next, when you see about x axis, it is not meeting, not parallel, So this is bending about x axis, this is bending about x axis. Next, if you see this beam, take any cross section, draw longitudinal axis, x axis and y axis. So you can see this axis is not parallel, not meeting for the load line. So it is bending about x for sure. Okay. Okay. Anyway, we have taken this as x direction. This will remain as x direction. Now this will become y, because out of the plane we have taken here x. We will maintain the same thing here also. Okay. Now if you assume this as y, this y axis, if you draw, it is meeting here. If you extend the y axis, it is meeting here. So about y you cannot get bending. Okay. Next, about z, if you see, it is parallel. Okay. So this axis is also bending about y. Okay. Next, we will come to this. Okay. Take any cross section, draw the three axes. Okay. First, it is meeting the z axis, so there will be no torsion. Next, this is parallel to y axis, there is no bending. If you see this axis, it is not meeting, not parallel, so this is also bending about y. Okay. So what does it mean? If you take a frame like this and you bend like this along, okay, along, so like this, okay, like this, this will simply bend, this will simply bend but not twist anywhere, because here you see the longitudinal axis is parallel, the longitudinal axis is meeting, the longitudinal axis is meeting. So everywhere there is no possibility of creating a torsion. Next, if you see the same frame with load lying out of the plane, okay, load out of the plane or along x, we can say, as we are taking along the length as z, okay, along out of the plane we will maintain as x. Okay. Now you see for this beam AB, CD, so for the beam AB, if you take any cross section and see the load, this is parallel, I can eliminate x, z, it is meeting the load line here, I can eliminate z. So the answer is it is bending about y axis now. Okay. Next we will see for this case, we will take a cross section here. Okay. Let me take this axis. So this is so I can take the axis anywhere along the length. Okay. So this I am taking as x, so this I will take as y, because out of the plane I am maintaining as x. Okay. So this I can take as y. Okay. There is no, even if you interchange x and y, bending will remain bending only, as we are maintaining z as longitudinal axis. Okay. Right. So this and this are parallel, the load is like this, x axis is like this, both are parallel, I can remove. Okay. Next, the load is like this, even if you extend this and extend the load line, it is not meeting anywhere, so it is having eccentricity about this load of this much eccentricity. Okay. Next, coming to torsional axis, this is not meeting the torsional axis also, so with respect to torsional axis also, this has an eccentricity. So this beam is subjected to both bending and torsion, bending and torsion. Next, coming to the third beam, so we have seen two beams, so first one only bending about x axis, second one bending about which axis, second one this is meeting, so the remaining x. Okay. So bending about x and torsion, torsion means default z. Okay. Next, third one, okay, load lying out of the plane. Okay. So the load is lying out of the plane, it cannot meet even on extension, it cannot be parallel even on extension, so it is having torsion for sure. Okay. Now take any cross section and draw remaining two axes. Y axis, is it meeting? No. Even on extension it won't meet, Is it parallel? No. So obviously it is bending about y. Next, bending about x, x-axis is parallel, x-axis is parallel to this, so you can directly eliminate the axis. So, this is bending about y and twisting as well, or torsion, both are same. Okay. So, just by changing the load, in the previous case if you see, the load was like this. So, if the load was like this is only bending, this is only bending, this is only bending. If the same load is applied along the x, then this is bending and twisting, this is bending and twisting. You can yourself imagine and feel the same. So, imagine there is a beam like this. Okay. So, if I apply the load out of the plane, so this is the plane, right, out of the plane load comes like this, within the load plane comes like this, because I assume this as plane. So, if within the plane I apply, everything bends without twist, you can imagine that, right, along the plane. So, everything gets bent, one will be in x, one will be in y, but it simply bends. So, there is a fixed beam here, I attached a rod, load within the plane. Now, if I apply the same load out of the plane, this will bend, this will twist, this will twist, you can imagine, right. So, by changing the load direction, some will be in bending, some will be in twisting. So, it is very difficult for you to identify which is in bending and which is in twisting. So, using this rule, it gets simplified. Okay. Now, I will show you this example physically. See, my frame is given like this, okay, which is fixed at this end. Okay, means I am holding this frame like this. Okay, I am folding this like this. In the first case, how is my load? It is downward towards the gravity. I am applying like this. So, if I apply like this, let me allow some deflection to feel the bending. Okay, I am applying the load downward. You can see there is no twisting anywhere in the beam. Okay, everything is simply rotating about the cross section. Okay, if I allow the deflection, you can feel that, right, only bending. Now, if you see, if I apply the same load in this direction, now you can see this will get twisted. You can feel that, right. So, this is twisting like this, instead of bending, this is getting twisted, you can feel that. So, if I apply a load like this will get twisted. Okay. So, if I am applying a load like this will get twisted, because of this will get twisted. If I apply a load like this, now you imagine this, right, if I apply a load, this is twisting. Now, imagine these two are fixed and applying a load like this. Okay. Now, you can imagine this is getting twisted. Okay. If I apply a load for this frame, this will get twisted. Just like free body diagram, if you remove this and bring the load like this, you can imagine, okay, this is also getting twisted. Okay. Suppose if I apply the load axially like this, then see, this is axial, there is no bending here, this is bending, this is bending. Even we can draw this with axis also. Third case, if I apply a load axial, wherever you draw the cross section, it is meeting all the axes. So, it is purely axial. Okay. Next, for this axis, if you extend the load line, okay, so it will definitely meet the longitudinal axis, no torsion. So, this is not meeting, not parallel. For this axis also it is not meeting and not parallel. Yeah, not parallel. So, it will get twisted. Okay. So, if you apply the load axially, in this direction, sorry. So, this is longitudinal axis, right, this will get meted. Okay. So, longitudinal axis is cancelled, this is x axis, bending axis. Okay. This is parallel to the load, this is eliminated. So, it is bending about x axis. Next, coming to this is the cross section. Okay. I will extend like this. So, it is meeting the load line, I can remove this. Next, this axis is perpendicular this, I can remove this, the only axis is bending. Okay. So, this is axial, this is bending about x, this is also bending about x. Okay. So, you can see if I apply the load like this, there is no turning. If I apply the load downward, downward, there is no twisting. If I apply the load away from the plane, you can feel it is getting twisted. It is getting twisted. This twist will continue here also, because you see, I will draw longitudinal axis for all the three. This is longitudinal, this is longitudinal, this is also longitudinal. Okay, this side it is better, you have a better view. All these three are longitudinal axis. You have to get the twist, you have to apply load in such a way that that load line will not parallel to longitudinal axis. So if I apply a load something like this at the center, obviously it is hitting the load line. If I am applying the load away from the center, then this also will get twisted. I hope you are able to see now. See, these are the three axes. If I apply a load here, I am showing, but here whether I am applying at center or not, I did not tell you. If I apply away from the center, then this also will get twisted, because it is not meeting the longitudinal axis, not parallel to longitudinal axis. Okay, so if I am applying here, then it is not meeting the longitudinal axis, not parallel to longitudinal axis, this will get twisted. Next, I am applying the load here, it is not meeting, not parallel, so this will get twisted. Okay. Similarly, if I apply a load like this, it is going along the longitudinal axis, no torsion. Next, this is meeting the longitudinal axis, no torsion. Next, this is parallel to longitudinal axis, so no torsion. So I apply a load like this, there will be no torsion in entire. Similarly, if I apply a load like this, for this longitudinal axis is parallel, for this it is meeting, for this also it will meet here, longitudinal axis. If you extend the longitudinal axis, it will meet. So if you apply a load like this, no torsion. If you apply a load like this, no torsion. If you apply a load out of the plane, then there will be torsion in these two. Here also, if you apply away from the center, then three beams will be in torsion. Okay. So this is how. So just to make you feel, I prepared this shape. Okay. So I hope now you are able to feel the torsion exactly. Even when you prepare a shape like this with any plastic body which will deform easily, you can really see the twist also. Okay. So if possible, in further classes with some sponges or foam which generally bends easily, or with plastic, if I am able to make such shapes, I will try to show the twist also to get better feel to you. Okay. So this is how we have to identify the torsion. Okay. So once we know whether a load is creating bending or it is creating torsion, then we can find, because of bending moment, what is the bending stress we get, because of torsion, what is the torsional stress we get, both we can find individually very easily. Okay. Identifying the formula is very easy, but finding whether this load, because the load is same, the same load creates bending, the same load creates torsion. Okay. So identifying this is very essential to understand classes further. Okay. Okay. So in the next class, because of the, so you already identified what is the, when you are getting torsion, what amount you are getting torsion, P into eccentricity. So because of the torsion, how much stress is generated along the cross section, that we will calculate in the next class. Okay.